The 23rd of July, 1944, dawned gray and ominous over the hedgerows of Normandy, where Sergeant Hans Müller sat in the commander's cupola of his Panzerkampfwagen V Tiger I, watching the horizon with growing unease. The 56-ton behemoth beneath him represented the pinnacle of German armored engineering. Its 88mm main gun could penetrate any Allied tank at ranges exceeding 2,000 meters, and its frontal armor, 100 millimeters thick, had proven nearly impervious to conventional anti-tank weapons. Yet Müller felt no comfort this morning, for he had heard the stories from other crews, tales of RAF Typhoon fighter bombers swooping from the clouds like mechanical hawks, unleashing rockets that struck with devastating force where traditional artillery and tank shells had failed. According to battlefield reports documented in the British War Office's operational research papers, the psychological impact of Typhoon attacks often exceeded their actual effectiveness, but the numbers told a different story. Each Typhoon carried 8 RP-3 rockets beneath its wings and guided projectiles tipped with 60-pound armor-piercing warheads that achieved penetration through entirely different physics than conventional tank ammunition. While a 75mm Sherman gun fired solid shot at velocities around 2,600 feet per second, relying on kinetic energy to punch through steel, the Typhoon's rockets employed something far more sinister: shape-charge technology that created a superheated jet of metal capable of burning through armor like a blowtorch through butter. The technical specifications were sobering. A standard American M61 armor-piercing shell from a Sherman tank could penetrate approximately 3 inches of steel at 500 yards, enough to threaten most German medium tanks but insufficient against the Tiger's glacis plate. The British 17-pounder anti-tank gun, widely regarded as one of the war's finest, managed roughly 5 inches of penetration under optimal conditions. Yet the RP-3 rocket's warhead, despite its relatively modest velocity of 1,500 feet per second, could theoretically penetrate up to 5 inches of armor from any angle, thanks to the Monroe effecta phenomenon, where explosive energy focused into a narrow stream achieved penetration far exceeding the warhead's physical dimensions. Müller had witnessed this principle's horrifying effectiveness 3 days prior near Villers-Bocage. His company had been advancing through an orchard when the distinctive roar of Napier Sabre engines announced the Typhoon's arrival. The first he knew of the attack was when Lieutenant Steiner's Tiger, positioned 200 meters to his left, erupted in flames. The rocket had struck the engine deck, the tank's most vulnerable surface, and the shape-charge jet had penetrated downward, igniting fuel and ammunition simultaneously. Steiner's crew had no chance. As referenced in Max Hastings' Overlord, D-Day and the Battle for Normandy, the Typhoon squadrons of the 2nd Tactical Air Force flew over 300 sorties daily during the Normandy campaign, and their primary targets were the feared Tigers and Panthers that threatened to stall the Allied advance. What made these attacks so devastating wasn't merely the rocket's penetrative capability, but their angle of attack. Tank designers focused protection forward, where enemy fire would most likely come from. But aircraft attacked from above, where armor was thinnest, typically 15 to 25 millimeters on the Tiger's engine deck and turret roof, compared to the 100mm frontal glacis. Müller checked his watch, 0730 hours. The morning patrol would begin soon, and with it, another day of watching the skies as carefully as the roads, knowing that the greatest threat to his invincible tank might come not from other tanks at all, but from the air itself. On the 14th of October 1943, Wing Commander Roland Beament throttled his Hawker Typhoon Mark E along the runway at RAF Tangmere, feeling the peculiar asymmetry of the 8 rocket projectiles slung beneath his wings. The Typhoon had been designed as an interceptor, meant to chase down Luftwaffe fighter bombers at low altitude, where its powerful Napier Sabre engine 24 cylinders arranged in an H configuration producing over 2,000 horsepower gave it devastating speed. Yet the aircraft had found its true calling in an entirely different role: ground attack. The question Beament and his colleagues at the Fighter Bomber Development Unit now sought to answer was whether this brutish, powerful fighter could become something unprecedented, a tank killer that struck from the sky. The concept wasn't entirely new. The Soviet Air Force had experimented with anti-tank rockets since 1941, and the Luftwaffe had deployed crude rocket-armed Stukas against Soviet armor. But the British RP-3, formally designated the rocket projectile's 3-inch, represented a quantum leap in sophistication. Developed at the Royal Aircraft Establishment in Farnborough, the weapon consisted of a steel tube 3 inches in diameter, filled with 11 pounds of cordite propellant, attached to either a 25-pound solid steel head for armor penetration or a 60-pound semi-armor-piercing high-explosive warhead. When fired, the rocket accelerated to 1,500 feet per second in 0.4 seconds, maintaining enough kinetic energy and explosive force to threaten even the heaviest German tanks. According to David C. Isby's Fighting the Bombers, the Luftwaffe's struggle against the Allied bomber offensive, the key innovation lay not in the rocket itself but in the delivery system. Unlike tank guns that fired on relatively flat trajectories, rockets could be launched in a shallow dive, allowing pilots to attack from angles that exploited tanks' weakest armor. The Typhoon's 8-rocket salvo, delivered from 1,000 feet at speeds exceeding 300 miles per hour, created a beaten zone approximately 70 feet wide and 100 feet long, enough to blanket a tank platoon with devastating effect. Beaumont's test that October afternoon demonstrated both the weapon's promise and its challenges. Diving at 45 degrees toward a captured Panzer IV positioned on the Salisbury Plain ranges, he triggered the rockets at 800 feet. The Typhoon shuddered as 4 projectiles streaked downward in pairs, their solid fuel motors leaving trails of white smoke. 2 missed entirely, victims of the weapon's notorious inaccuracy. A third struck the ground 30 feet short, its warhead detonating harmlessly, but the 4th hit the Panzer's turret dead center. The 60-pound warhead detonated on impact, and the armor-piercing penetrator Cora hardened steel plug behind the explosive charge punched through 50 millimeters of steel as though it were cardboard. Inside the turret, the effect would have been catastrophic: spalling metal fragments, explosive overpressure, and the penetrator itself ricocheting through the fighting compartment. The trials continued through November and December of 1943, with British scientists meticulously documenting each attack. They discovered that the RP-3's effectiveness depended heavily on impact angle. A rocket striking at 90 degrees perpendicular to the armor achieved maximum penetration, potentially defeating up to 130 millimeters of steel when using the shape charge effect. But hits at oblique angles, common in combat, significantly reduced penetration. A strike at 30 degrees might barely scratch a Tiger's frontal armor. This explains why Typhoon pilots received extensive training to attack from specific angles, ideally targeting engine decks, turret roof, and side armor where thickness ranged from 25 to 80 millimeters, well within the RPS defeat envelope. By January of 1944, the RAF had committed to mass production. Factories across Britain churned out RP-3 rockets by the thousands, while Typhoon squadrons underwent intensive training in rocket attacks. Number 181 Squadron, commanded by squadron leader David Scott Malden, became the first operational unit to receive the weapon in February 1944. Scott Malden's pilots practiced relentlessly against mock targets in the Welsh Hills, perfecting the shallow dive attack profile that would become the Typhoon's signature tactic. What emerged wasn't merely a new weapon system, but a new philosophy of armored warfare. For the first time, tanks faced a credible threat from above, one that exploited vulnerabilities their designers had never adequately addressed because aircraft had previously lacked the weapons to penetrate heavy armor reliably. In a classified laboratory at Fort Halstead, Kent, on the 9th of March 1944, Dr. Charles Denistone Burney examined the steel test plate before him with satisfaction. The plate, 100 millimeters thick and taken from a captured Tiger I, bore a perfectly circular hole 3 inches in diameter, its edges heat-warped and discolored. This wasn't the clean puncture created by kinetic penetrator's solid shot that relied purely on mass and velocity to punch through armor. This was something far more interesting. a shaped charge penetration, achieved by the RP-3 rocket's warhead using principles that seemed to defy common intuition about how explosives interacted with metal. The physics underlying shaped charges dated back to 1888, when American scientist Charles Munro discovered that explosives detonated in contact with surfaces produced dramatically enhanced cutting effects when the explosive charge contained a cavity. This Munro effect, refined by Swiss scientist Henry Mohopt in the 1930s, worked through a remarkable process. When a hollow charge warhead detonated, the explosive liner, typically copper or steel, collapsed inward at velocities exceeding 20,000 feet per second. The liner's material didn't melt in the traditional sense, but instead transformed into a superplastic jet that behaved almost like a fluid, despite temperatures reaching several thousand degrees Celsius. As documented in technical reports from the Ministry of Supply's Armament Research Department, this jet possessed extraordinary penetrative capability. Unlike a tank shell that must physically push through armor, a process limited by the projectile's material strength, the shaped charge jet burned through steel via plastic deformation and hydrodynamic flow. The jet's velocity and density created pressures exceeding 1 million pounds per square inch at the penetration point, enough to force the armor to flow aside like water parting before a speedboat's prow. The implications for tank warfare were profound. Traditional armor protection followed simple logic. Thicker plates defeated projectiles with insufficient kinetic energy to penetrate. Angling armor increased its effective thickness. A 60mm plate sloped at 45 degrees presented approximately 85 millimeters of effective thickness to an incoming round. This principle explained the Tiger Eye's formidable reputation. Its frontal armor, though only 100 millimeters thick, was perfectly vertical, but the sheer mass of steel, combined with the 88mm gun's ability to kill Allied tanks beyond their effective return fire range, made it nearly invulnerable in frontal engagements. Shaped charges changed this calculus. Because penetration depended on the explosive jet's velocity and focus rather than kinetic energy, armor thickness mattered less than the standoff distance, the gap between the warhead and target when detonation occurred. The RP-3's 60-pound warhead contained approximately 5 pounds of RDX explosive arranged around a mild steel cone. When detonated at optimal standoff, typically 6 to 12 inches, the collapsing liner produced a jet moving at approximately 30,000 feet per second, with effective penetration of up to 5 inches of homogeneous steel. Dr. Burney's experiments revealed why Typhoon rockets proved so effective against Tigers despite the latter's reputation for invincibility. A 75mm Sherman round striking a Tiger's frontal armor at 500 yards delivered roughly 1.3 million foot-pounds of kinetic energy. This sounds impressive until one calculates the physics. The round's relatively small diameter concentrated this energy over approximately 4 square inches, producing insufficient pressure to penetrate homogeneous armor 100 millimeters thick. The projectile might crack the armor, cause spalling on the interior surface, or even embed itself partially, but complete penetration at combat ranges remained unlikely. The RP-3 approached the problem differently. Its shaped charge jet concentrated approximately 800,000 foot-pounds of energy less than the Sherman's round into an area measuring roughly 0.75 inches in diameter. This concentration produced pressures exceeding 3 million pounds per square inch at the penetration point, more than sufficient to defeat the Tiger's engine deck armor of 25 millimeters or even the turret roof's 40 millimeters. Furthermore, the jet's penetration was relatively insensitive to impact angle up to about 30 degrees from perpendicular, meaning rockets striking from above retained effectiveness even when hitting sloped surfaces. According to Anthony Tucker-Jones' Armored Warfare in the Battle for Normandy, British operational research teams documented that Typhoon rocket attacks achieved approximately 4% direct hits against armored vehicles, seemingly poor accuracy, but devastating when one considers that each Typhoon carried 8 rockets and typically attacked in flights of 4 to 8 aircraft. A single squadron attack thus delivered 32 to 64 rockets against a target area, virtually guaranteeing multiple hits. Squadron leader John Robert Baldwin checked his oxygen mask seal and scanned the sky above the Falaise pocket on the 7th of August, 1944, leading 8 Typhoons from No. 197 Squadron toward what intelligence described as a major German armored concentration. Below, the Norman countryside had transformed into a nightmare landscape of burning vehicles, cratered roads, and desperate Wehrmacht units attempting to escape the Allied encirclement. Baldwin's mission was simple in concept, terrifying in execution. Find the Tiger tanks of the 1st SS Panzer Corps and destroy them before they could break through the Allied lines. The Typhoon was not a forgiving aircraft. Its Napier Sabre engine, while powerful, suffered from chronic reliability issues, coolant leaks, bearing failures, and a tendency to shed propeller blades at inopportune moments. The massive 24-cylinder power plant vibrated intensely, making long flights exhausting for pilots. Visibility from the cockpit was mediocre at best, with the long nose and thick canopy framing restricting forward and upward views. Yet the aircraft possessed virtues that made it ideal for ground attack. Tremendous speed at low altitude, over 400 miles per hour, in level flight, exceptional stability as a gun platform, and the ability to carry 4,000 pounds of ordnance, whether bombs, rockets, or a devastating combination of both. Baldwin spotted them at 11:30 hours. 6 Tigers advancing in line ahead formation along a sunken road northwest of Trun, their commanders' heads visible above the turrets as they scanned for threats. The tanks moved cautiously, stopping frequently to let their commanders glass the hedgerows with binocular standard procedure after countless, ambushed by British anti-tank guns. But the German crews were looking horizontally, not vertically. That fatal oversight gave Baldwin his opening. He keyed his radio. "Tally-ho, Tigers at 10 o'clock low. Line astern for the attack." "I'll take the leader," his wingman acknowledged. Their Typhoons forming into attack interval sufficient spacing to avoid each other's rocket trails while maintaining mutual fire support. Baldwin rolled left, pushed the stick forward, and dove toward the lead Tiger from 4,000 feet. The Sabre engine's roar intensified as airspeed built, 250 miles per hour, 300-350. The Tiger grew in his gun sight, a gray-green rectangle with the distinctive stepped hull and massive turret of the Mark I variant, according to Norman Franks. Typhoon attack, the legendary British fighter in combat in World War II. The approved attack profile called for a 30-degree dive angle, rocket release at 1,000 feet, and immediate pull-up to avoid ground fire. Baldwin followed the doctrine precisely, his right thumb hovering over the rocket release button on his control column. At 1,200 feet, he centered the gun sight's illuminated pipper on the Tiger's engine deck, the rectangle of louvered metal covering the engine compartment, the tank's most vulnerable surface. Time seemed to slow as his thumb pressed the release. The Typhoon shuddered violently as 4 rockets ignited simultaneously, firing all 8. At once risked structural damage, their white smoke trails obscuring his vision momentarily. He counted 2 seconds, then triggered the second salvo. The remaining 4 rockets leaped from their rails as Baldwin hauled back on the stick, pulling 4 Gs, his vision graying at the edges as blood drained from his brain. The Typhoon clawed upward, engine howling at maximum power. Behind him, the rockets completed their 1.5-second flight. The first struck 15 feet short, detonating in the dirt road with a thunderous crash that showered the Tiger with rocks and shrapnel, but caused no damage. The second and third also missed, one passing over the turret by inches, the other striking a tree. But the fourth rocket hit the engine deck 10 feet behind the turret, exactly where Baldwin had aimed. The 60-pound warhead detonated on contact, its shaped charge penetrator burning through 25 millimeters of steel in microseconds. The superheated jet lanced into the engine compartment, igniting fuel lines and hydraulic fluid instantly. For Sergeant Hans Muller, commanding the Tiger, the first indication of disaster was a tremendous bang followed by complete loss of electrical power. Then came the smoke, thick, black, toxic smoke boiling up from the engine deck, filling the turret through every opening. Muller screamed orders, "Bail out! Bail out!" His driver and radio operator already had their hatches open, tumbling out as flames erupted from the engine compartment. Muller threw himself through the commander's hatch as ammunition in the turret. Bussell began cooking off 75 rounds of 88mm shells, detonating in a rippling series of explosions that tore the turret completely free of its ring. The Tiger had transformed from an unstoppable war machine into a funeral pyre in less than 30 seconds. 4 crew members escaped. The bow gunner, trapped by jammed hatches as flames filled the forward hull, did not. Baldwin's wingmen attacked the remaining Tigers with similarly devastating results. Flight Lieutenant Peter Brooker's rockets struck the second tank's right track, immobilizing it and setting it ablaze. The third Tiger's commander, Oberfeldwebel Ernst Becker, managed to deploy smoke grenades and reverse into a copse of trees, but not before 2 rockets struck his tank's turret, killing his gunner and loader instantly. On the morning of the 15th of August, 1944, Generalmajor Kurt Meyer stood in the command post of the 12th SS Panzer Division Hitlerjugend, studying casualty reports that read like a butcher's ledger. In 72 hours of fighting withdrawal from Falaise, his division had lost 43 tanks, 19 Panthers, 8 Panzer IVs, and 6 precious Tigers. Of these losses, aerial attack accounted for 27, rockets from RAF Typhoons and P-47 Thunderbolts of the American 9th Air Force, the numbers represented more than tactical setbacks. They indicated a fundamental shift in armored warfare that German doctrine had failed to anticipate. Meyer, at 33 the youngest divisional commander in the Wehrmacht, had built his reputation on aggressive mobile warfare, the kind of lightning strikes that had shattered Soviet armies in 1941 and British forces in North Africa. But Normandy had revealed a new reality. Allied air superiority was absolute, and German armor could no longer maneuver freely in daylight without suffering catastrophic casualties. As documented in Samuel W. Mitchum Jr.'s Retreat to the Reich, the German defeat in France, 1944, Meyer's division, which had begun the Normandy campaign with 150 tanks, now fielded fewer than 30 operational vehicles. The psychological impact on tank crews was devastating. Oberleutnant Michael Wittmann, commander of No. 1's 01 Heavy Panzer Battalion and Germany's most celebrated tank ace, with 138 confirmed kills, had been killed by rocket-firing Typhoons near Saint-Aignan-de-Cramasnil on the 8th of August. Wittmann's death, his Tiger struck simultaneously by multiple rockets that penetrated the turret roof and detonated the ammunition, sent shockwaves through the Panzerwaffe. If the Wehrmacht's greatest tank commander could be destroyed so easily from the air, what chance did ordinary crews have? The problem went beyond individual losses. German tank doctrine emphasized offensive action, rapid advances exploiting breakthrough points, envelopment of enemy positions, aggressive counterattacks against Allied penetrations. All these tactics required daylight movement, preferably across open terrain where the Tigers' and Panthers' superior guns could engage at maximum range. But Allied air power had made such operations suicidal. Rocket-armed fighter bombers patrolled constantly during daylight hours, typically operating in cab ranks flights stacked at different altitudes, waiting for ground controllers to vector them onto targets. Meyer understood the technical reasons for his tank's vulnerability. He had examined the wreckage of destroyed Tigers, noting how rockets consistently penetrated the engine deck and turret roof where armor thickness ranged from 25 to 40 millimeters, sufficient against artillery fragments, but inadequate against shape-charge warheads. Some crews had tried improvised countermeasures, welding additional armor plates to vulnerable surfaces, mounting spare track links on engine decks, even applying concrete to the turret roof. These modifications added weight that stressed already overtaxed suspensions and transmissions, reduced mobility, and proved largely ineffective. A shaped charge jet capable of penetrating 120 millimeters of steel wasn't meaningfully degraded by an extra 20 millimeters of improvised armor. According to Steven Zaloga's Armored Thunderbolt, the U.S. Army Sherman in World War II, German intelligence had initially dismissed Allied claims about Typhoon effectiveness as propaganda. Operational analysis suggested that actual kill rates were perhaps 10% of claimed figures. Pilots often reported tanks as destroyed when they were merely damaged or abandoned. But even accepting conservative estimates, the impact was severe. A Tiger cost approximately 300,000 Reichsmarks to produce and required 6 months of manufacturing time involving hundreds of specialized workers. Each loss represented an irreplaceable drain on Germany's dwindling industrial capacity. More crucially, the Typhoon threat forced tactical adaptations that negated German armor's advantages. Tanks increasingly moved only at night or in terrible weather when Allied aircraft couldn't fly. They dispersed widely rather than concentrating for maximum combat power. They spent more time hidden in woods and villages than maneuvering in open country. These defensive measures kept tanks alive but rendered them largely ineffective. A Tiger hidden in a barn couldn't support an infantry attack or counterthrust against Allied penetrations. The human cost was equally severe. Tank crews operated under constant psychological strain, knowing death could strike without warning from above. Unlike infantry who could hear artillery shells incoming or see enemy tanks at range, tankers had almost no warning before rocket attacks. The first indication was often the rocket's impact, by which point survival depended purely on luck. This created endemic stress that manifested in declining combat effectiveness, increased desertion rates, and widespread fatigue among veterans. Meyer recognized that Germany faced an unsolvable dilemma. Producing more Tigers wouldn't help if they remained vulnerable to air attack. Developing improved anti-aircraft defenses for tanks was theoretically possible some late war. German designs included remotely operated machine guns for anti-aircraft defense, but such systems offered little protection against high-speed fighter bombers attacking from multiple directions simultaneously. The fundamental problem was that aircraft could choose when and where to attack, exploiting momentary gaps in defensive coverage, while tanks could only react. On a surprisingly cold morning, the 23rd of September, 1944, Captain Peter Johnson of No. 2 Operational Research Section, 2nd Tactical Air Force, walked among the hulks of destroyed German tanks scattered across a field near Chambois, France, clipboard in hand and skepticism firmly in place. His mission, unglamorous but critical, was determining how these vehicles had actually died, as opposed to how their destroyers claimed they had died. The distinction mattered enormously for understanding the true effectiveness of RAF Typhoons and their vaunted rocket projectiles. Johnson's preliminary findings, which would later form part of a classified report to Air Ministry, painted a picture considerably more complex than the triumphant narratives appearing in newspapers. Of the 53 destroyed German tanks he had examined over the past week, only 9 showed definitive evidence of aerial rocket penetration. 11 had been destroyed by ground fire, primarily anti-tank guns and tank destroyers. 14 appeared to have been abandoned by their crews intact and subsequently destroyed by demolition charges or air attack after evacuation. The remaining 19 showed battle damage too extensive to determine the killing blow, having been struck by multiple weapon systems including artillery, rockets, and bombs. This was not to suggest Typhoons were ineffective, merely that their effectiveness manifested differently than pilots' combat reports indicated. As documented in Lee Heaver's Typhoon, the Hawker Typhoon's finest hour over Normandy, RAF pilots claimed approximately 600 German armored vehicles destroyed during the Normandy campaign. Careful analysis by operational research teams reduced this figure to approximately 140 confirmed kills still. Impressive, but representing less than 25% of claimed totals. The gap between claims and reality stemmed from combat conditions. Pilots attacking at 300 miles per hour while being shot at by machine guns and anti-aircraft artillery couldn't accurately assess results. A tank hit by rockets might emit smoke from engine damage, appearing destroyed, but remain operational after repairs. Abandoned tanks clustered near bridges or in defiles appeared to be victims of air attack when they'd actually been disabled by mechanical failures, fuel shortages, or deliberate destruction by retreating crews. Multiple aircraft attacking the same target area might each claim the same kill. Yet Johnson's investigation also revealed why Typhoon attacks had such devastating strategic impact despite modest kill rates. The threat of air attack paralyzed German armor during daylight hours. Interviews with captured German officers revealed that tank units spent an average of 16 hours per day hidden in forests. villages or under camouflage netting, and only 8 hours maneuvering or fighting. This ratio reversed the normal operational tempo. Tanks became defensive weapons rather than offensive shock forces. The psychological damage was equally significant. A study conducted by British Army psychiatrists examining captured German tank crews found that approximately 40% suffered symptoms consistent with combat stress, reactions significantly higher than infantry captured during the same period. Many crews described overwhelming anxiety when forced to move in daylight, with some admitting to deliberately stalling or breaking down their vehicles rather than advancing across open terrain. According to Alexander McKee's Anvil of Victory, the most devastating Typhoon missions often involved few or no confirmed kills, but achieved operational paralysis through psychological pressure. On the 18th of July, during Operation Goodwood, RAF Typhoons flew over 200 sorties against German armor southeast of Cannes. Post-battle analysis confirmed only 11 German tanks destroyed by rockets. Yet the surviving German commanders reported that constant air attacks forced them to remain concealed, prevented ammunition resupply, and delayed counterattacks by 6 to 8 hours, enough time for British forces to consolidate gains that might otherwise have been reversed. Johnson's research also explored why shaped charge rockets achieved lower kill rates than theoretical penetration suggested. The primary factor was accuracy. The RP-3 was an unguided ballistic weapon launched from an unstable platform. Fighter bomber traveling at 300 miles per hour while diving at 30 degrees and being subjected to ground fire. Small variations in launch angle, airspeed, or release altitude created large trajectory deviations at impact. Even skilled pilots achieved only 8 to 10% hit rates against stationary targets on ranges. Combat accuracy dropped to 4% or less. Furthermore, a hit didn't guarantee penetration. If a rocket struck at an oblique angle more than 30 degrees from perpendicular, the shaped charge jet often failed to form properly, resulting in surface damage rather than penetration. The